Okay, welcome to Robotics 1. In last class, I talked about 4 rules for kinematic analysis. And I'm going to rewrite those rules. So rules. First rule is joint articulation axis. Second rule, xn axis is perpendicular to Zn and Zn minus 1. In the last class, I actually combined the third and the second rule. So, but if you look at the textbook, they specify those rules must intersect Zn and Zn minus 1. And the last rule is right hand coordinate system. So now what we are going to do is I'm going to rework the problem that I started. I will set up the problem here. I would explain the problem again, and I would work out that problem in MATLAB. So let's start with the problem that we were trying to solve in last class. So if you think about it, we have a revolute joint. There is another revolute joint. And there is the end effector. So I'm gonna rewrite this as R, because you have the first revolute joint parallel to R. Now, first and foremost, applying rule number 1, I need to specify the 0th frame. So this is the 0th frame. This is the first frame. And I'm gonna add a second frame over here. This is the end effector. This is Z0, Z1. Please note, for Z2, there is no articulation. But if we were to take Z2 parallel to Z1, that would make our life very easy. So if you don't have any constraint, I would recommend make sure that the frames are aligned. Then there is no constraint on X0, but I'm just going to have my X0 over here. And right hand coordinate system, X, Z, so I have Y. So this is going to be my Y0. And this is exactly what we did in last class. Here, X1, Y1. And here, X2 and Y2. Any questions about the frames? This is the most important step when we are going to solve the forward kinematics problem. And you would realize that other steps are pretty straightforward. Curl your fingers in the direction of Z0. That gives me the positive rotation. So this is theta 1. Curl your fingers in the direction of Z1. That gives me positive rotation. How about joint? So don't worry about it. Everyone understood? Now what I'm going to do is, uh, and I want you to follow this step very carefully, because for this problem, it may look simple, but for the next problems or next few problems, this step is going to become very, very important and may seem complicated. So remember, I'm going to start with my rotation matrix R01. R01 means the rotation of the frame 1 with respect to frame 0. This rotation matrix, remember, the only rotation matrix that we have to remember is this one. 0, 0, 0, 0, 1. What does this rotation matrix say? This is the projection of rotated frame onto the base frame. Now, so I'm gonna write this down here. This is x naught, this is y naught, and I want to add x1, y1, z1. So I want you to look at x1. X1 is parallel to x naught. So which means there is 1 here. 0, 0. Y1 is parallel to y naught, which means 0, 1, 0. And Z1 is parallel to Z naught. So I have 0, 0, 1. So what we have here is the projection of x1 onto x0, projection of y1 into z0. Everyone understood this? But please recognize, this is an identity matrix. And for identity matrix, multiplication does not matter. So what I'm going to get is 0R1 is going to be cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Agreed? Next step is I need to construct something called as the homogeneous transformation matrix. If you look at the classic books on robotics, they will spend 3 to 4 pages discussing homogeneous transformation matrix. Has anyone taken robotics before? No? Yeah, good. So homogeneous transfer, and you can relate to this pain and suffering. So basically, you will have 3 to 4 pages talking about homogeneous transformation matrix. But you don't have to follow that. So remember, homogeneous transformation matrix is a 4 by 4 matrix. Homogeneous transformation matrix is a 4 by 4 matrix. In that 4 by 4 matrix, first 3 by 3 matrix is going to be rotation transformation 0. Just copy and paste 0, 0, 1. Everyone agreed? So whatever we had here, it went over here. Last row 0, 0, 0, 1. Now here comes the most important and tricky part. Check this out. This frame is 0. So this is x0, y0, and z0. Now what I want you to do is, we need to find out, and this is very important, the location of frame 1 with respect to frame 0 in the 0th coordinate frame. I will repeat this once again. So now I want you to observe that my frame number 1 is at some offset distances from frame 0. Do you agree with me? Now I need to find out what is the position of frame 1 with respect to frame 0. Everyone understood this? Clearly, if I want to travel from frame 0 to frame 1, you can observe I need to go up by distance A1, and then I need to go right by distance A2. But I want position. So I want the position with respect to the 0th frame. So what would be the easy part? So you agree with me, and I'm going to write this down. To go from 0 to G1, I need to go distance A1. Are you with me?
Yes.
Now, what I want to do is, I want to go, and actually I need more space here, and it will be super clear in just a second. To go from 0 frame to 1 frame, I can just say, and this is super important, so please pay attention. Pins down, attention on board. So I can just say, look, hey, this is easy. This is A2 and 0. Do you agree with me?
How is that?
Because.
Oh, on the X. Okay, I see it. Sorry, I'm a little late.
No worries. Is this correct?
Well, it makes sense because A1, you're going along the Z-axis. A2, you're going along the X-axis, and nothing's going along the Y-axis, right?
Correct. Imagine this is fine when your theta 1 is 0. For a minute, visualize your theta 1 gets rotated. If your theta 1 gets rotated, do you agree with me? In that particular case, I will have to take components of A2 on X0 axis and component of A2 on Y0 axis. So because robot is going to rotate in 3 dimensions. So which means when I write these positions, I need to make sure that this equation is valid for all values of theta. What I mean by that, and you will realize this in just a second, I need to write this is A2 cosine theta 1, A2 sine theta 1. And now understand when theta 1 is 0, which is the case in point, I get A2 as the x0 distance and 0 as the y0 distance. I will give you a minute to think about it. So understand that this is the key part. Whenever you have homogeneous transformation, this is the position between frame 1 and frame 0 for all values of theta, which means if theta is equal to 0, you see that this cosine theta is going to become 1, sine theta is going to become 0. Fine. If this is 90 degrees, and I want you to visualize for a second what it means by 90 degrees. This means this robot, this first joint, has rotated in the plane of, it's rotated. The plane is rotated by 90 degrees. At that time, the first term will become 0, but the second term will be positive. Do you agree with me? Let's look at additional case wherein this robot has rotated by 180 degrees. And if you rotate again by 360, again, the signs will take care of themselves. You agree with me? This is super important. And that's all you need to know from those 4 pages talking about homogeneous transformation. Everyone understood this? Problem solved.
I'm still not understanding how the one A2 sine theta 1. Why? How does that fit there?
Okay, I'm carrying my iPad with me because this is where it's being recorded. So I need. Okay, so what I'm gonna do just for you, let's look from top. Look from top. And you would notice, as soon as I look from top, I see x0, I see y0. And the robot arm, the way it is drawn, is like this, right? But when theta changes, this robot arm would go here. This distance is going to become A2, which means the projection of the robot arm on X is going to become A2 cosine theta 1. Yeah. Okay. And projection of robot arm on Y is going to become A2 sine theta 1. Any other questions? Online? Okay. Unfortunately, bad things start happening when you become cross code. Okay. No, that is not how we do it. Because I will try to explain this. So the rotation matrix is actually talking about the relative rotation between the frames. The rotation matrix does not give us any information about the relative position. But homogeneous transformation matrix includes position and rotation. That's why we need to have that last column. Does that answer your question? Fourth row, can someone tell me what does the fourth row signify? I'll write this again. Position of frame 2 with respect to frame 1. And what does this fourth row represent? The fourth row represents so that we can perform matrix multiplication. Oh, by the way, on the record, it's not perspective, okay? Okay. Now what I'm going to do is, I want you to think about this problem for a minute and understand that, okay, I'll work out this problem again, no problem. So what I want to do now is I went from frame 0 to frame 1. Now I want to go from frame 1 to frame 2. To go from frame 1 to frame 2, same drill. The rotation is about z-axis, but it's z1 axis. Do you agree with me? Cosine theta 2, sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. The next part is the rotation matrix, and I'm going to draw the robot again so that it would be clear. Because our first few robots, we may have to actually do this exercise in detail. And once you are familiar, and I promise you, you will be after 7-8 problems, you can just look at the robot and write down the homogeneous transformation matrices. Z1, X1, Y1. This is the end effector. Z2, X2, Y2. Do you agree with me? Yeah. Now, this projection matrix, please understand, my base frame is 1. Second frame is 2. So this is the projection of x2, y2, z2 onto x1, y1, z1. I know it may sound trivial. Can someone tell me what is the projection matrix? Correct, but still I will do it. X2 is in the same direction as x1. Some of me ask me what happens when theta is non-zero, when theta rotates. Whenever we are trying to solve the projection matrix, we would always assume that the robot is in fully extended equilibrium position. Okay, so don't worry about rotation. The rotations will take care of themselves. The next is this, and the last is this. So can I just go ahead and write this down? 0, 1, 0, 0, 0, 1, which means 1 R2 is going to be cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Yeah. Usually what I do is, and you will realize that I actually at this point, I directly go forming the homogeneous. Let me do it like this, just for first couple of problems. So now I need to write homogeneous transformation matrices. Minus sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, and 1. Now, I want to ask you, can you quickly tell me, I'm going to give you some A2, so I'll give you say A3 and A4 here. This is A3, and this is A4. So I would say, and you can correct me if I'm wrong, I'll write this here, A3, A4, A3, but please note, this is going to be X1, Y1, Z1. Why? Because we are dealing with previous frame, which is 1. Here, it's going to become A4 cosine theta 2, A4 sine theta 2. Agreed? Everyone understood this?
Yes. Yeah.
Forward kinematic problem is solved. What I mean by that? What it means is my homogeneous transformation. So I want to find out the position of end effector with respect to base frame. So I want to find out where this end effector is, with respect to the base frame. Base frame is called inertial frame. This frame is fixed, and sometimes it's denoted like this. This is called as the inertial frame. Remember this. Everything we do with respect to inertial frame, because that makes our life easy. So, and I'm gonna rewrite this. I want to find out 0H3. 0H2. I don't have 3. 0H2. 0H2 is 0H1 multiplied by 1H2. So if I multiply this 4 by 4 matrix by this under 4 by 4 matrix, I'm gonna get a 4 by 4 matrix. Do you agree with me? And I'm gonna go ahead and describe what that 4 by 4 matrix would look like. 4 by 4 matrix would have the structure similar to the homogeneous transformation that we talked about, 0, 0, 0, 1. Once again, this is with respect to x0, y0, z0. yx0, y0, z0, because our base frame is x1, x0, y0, and z0. And what I have here is 0, r2. And what I have here is the position of end effector in x0 direction, position of end effector in y0 direction, position of end effector in z0 direction. So I'm going to write it down here. Position of end effector along x0. Position of end effector along y0. This is position of end effector along z0. And this one doesn't matter. Everyone understood this? Everyone understood this? All right. So let me kind of go a step further and teach you the velocity analysis. At this point, what I have equations for positions. Do you agree with me? Yeah. If I take the derivatives of those, I'm going to get velocity of the end effector along x0, y0, z0. Everyone understood this? That is the whole velocity analysis. Then I would take the double differentiation and I would find out the acceleration of the end effector. Do you agree with me? Yes. And last but not least, what I would do is I would use Newton's law, force is equal to mass times acceleration. And that is the dynamic analysis of end effector. And that is all there to it in robotics 1. Yes.
Then what is that?
Can you repeat the question?
What is that? I think that is a physical equation.
This is Newton's second law.
Why would you use that?
Because we need to find out the relationship between the force. At the end, we need to find out the differential equation of motion. So acceleration is the second derivative of position. The mass, and I'm just talking about translation, and you have force. So if you want to find out what are the forces on the end effector, or how much of force end effector can apply, what type of control I want to use, then you have to use Newton's second law. It is cumbersome. That's why we use something called as the Lagrangian method, because you can actually code it and you can get the equations automatically. You can get the plot simulations automatically. But this is what you have learned. Everyone understood this? Yeah.
So coming to the mass, so the mass to be calculated from the revolute joint, or
no, we are not there yet. So I will talk about mass, moment of inertia, inertia tensor, and all that stuff. So step by step. But I just want to tell you, this is what there is in robotics 1. Oh yeah, this is the time. Ooh, yeah, it makes more sense. Okay, wait for the next stuff that I'm going to talk about. It's more, even actually it will make more sense. Everyone knows Newton's second law. Do you agree with me? Does anyone know Radkar's first law? That is the corollary. I'm not kidding. That is the corollary of Newton's second law. And that law is written something like this. And I'm serious. I'm not joking. If you take the derivative of Newton's second law, you get F dot, mass is constant, M, acceleration dot. Do you agree with me? What is this? This is impulse. And what is this? This is jerk. This is the perfect time to introduce Redcar's first law. That goes like this. Sometimes to get things moving, you need a jerk. Sometimes to get the things moving, you need a jerk, which means if your robot is stuck, what would you do? Take a hammer and hit it. That is exactly what you are doing by applying impulse. And in life, unfortunately, sometimes to get things moving, you have to be a jerk. Based on my experience, story of my life. All right. Any other comments from my online students? Now, what I'm going to do is, clearly, I need to multiply two matrices, and I'm lazy, so I'm going to use MATLAB. But if you do not have MATLAB, I promise you, this multiplication is not hard because there are a bunch of zeros. But before I go to the MATLAB, unfortunately, I'll tell you, this is what's going to happen. I'm going to switch my screen. So which means I won't be able to show you the formulation and the MATLAB script at the same time. So I want you for a minute to look at what I have done so that when I start working in the MATLAB, you have the rotation matrices in front of you when we code. So online students, get MATLAB up and running. Switching screen. Okay, I worked this problem out before coming, but what I'm gonna do is, I'm gonna rework this problem. And in case if I get stuck or make a mistake, I can look at the solution. So if you are with me, first and foremost, let's start with a comment. This robot is R parallel R forward kinematics. Now, yeah. Yes, actually, you are right. Thank you. I should have done that. And if I don't do it, make sure next time. Is it good enough or need it bigger? So let me see font. Is this okay? Okay. Forward kinematics. So what you need to do is, first you need to define the symbolic variables. And I trust you know what the symbolic variables are. Command is syms. And our symbolic variables are, and this is the right point to go and look at what our symbolic variables are. A1, A2, A3, A4. These are the link lengths. Then I have theta 1, theta 2. These are the angles. Then I need to define the first homogeneous transformation matrix. Unfortunately, MATLAB will not allow you a variable naming 0h1. So I'm going to write h01. This is going to be my first homogeneous transformation matrix. This is going to be cosine theta 1 minus sine theta 1. Then I'm going to have 0. And then I'm going to have A2 multiplied by cosine theta 1. Then I'm going to add and so on so that I can type this properly. Sine theta 1 cosine theta 1 0 A2 sine theta 1. and so on. Last, 0, 0, 0, A1, and so on. Then 0, 0, 1, oh, sorry, 0, 1. So, what? Yeah, actually, I made a mistake here. 1, correct. Everyone understood this? I'm going to be lazy and I'm going to copy. I want you to see the notes. Can you see that your H01 is similar to H12, except now I have theta 2, copy, paste. So I'm going to make changes 1 to 2, right? This is going to become theta 2, theta 2. A2 is going to become A4, cosine theta 2, sine theta 2. And let's not forget to change here, just to make them look good. A3, A1 will become A3. A4, yeah, here is A4. All right. Any questions? Then I'm gonna do the multiplication. H03 is equal to H02 is equal to H01 multiplied by H12, right? And I'm just gonna say clear all, so that I do not have any variables in my workspace. Now, assuming I did not make any mistake, I would run this. And this is what I have. Believe it or not, this is the solution of the forward kinematics problem. What does this tell me? It tells me that first 3x3 matrix from here to here is basically my rotation solution, which means it is the orientation of the end effector with respect to the base frame. Orientation of the end effector with respect to the base frame. And the last column is nothing but of respect to inertial frame. Now I want you, it's difficult to show the entire expression in one go, but I want you for a minute to look at this big expression which is right here. You can see that my Z, the position of Z2 with respect to Z0 makes kind of sense, because we first go up by A1, then go up by A3. This makes sense. But somehow I'm not able to interpret what these other values are. So what I'm going to do is I'm going to simplify and try to see if it provides me with some sort of easier geometric interpretation. So I'm going to simplify. I'm going to enter. And then once you go on to the right, you will realize that your expression, so H02 expression, is kind of simplified further. So if you look at H01, actually, let me do it something like this so that you will see pitch 0 2. So you would see okay. Now I want to stop here for a minute and make sure that you have the same solution as I do, because this has a very nice physical interpretation. Can you see that whole big expression got reduced into a matrix where this first 3 by 3 matrix, tells me the orientation of the end effector in the base frame. Orientation of the end effector in the base frame. That is super important. And if you recollect, so there are different ways of representing this rotation. This rotation is simply represented in terms of θ1 and θ2. But you will see that you can take this rotation matrix, you can take this simple rotation matrix and convert that into roll pitch yaw, Euler angles, or you can convert that into Coutonians. And the good news here is this rotation matrix does not suffer from any singularities. So the solution is always valid. However, if you were to choose Euler angle, then you will realize that in certain cases, you would hit singularities. Now, as a word of caution, whenever you work out a forward kinematics problem, you should try to provide some sort of geometric interpretation. I mean, just don't trust the answer that you are getting from the solution. But at this point, I want to clarify a few things. Can you see that I have A2 cosine θ1, A2 sine θ1, I have A4 multiplied by, this is very important, cosine of θ1 plus θ2, A4 multiplied by sine of θ1 plus θ2. You agree with me? So there is some geometric explanation to this, which means what this is telling me that my end effector along x0 is at this position. This is the distance between the 0th frame and the second frame along x0. This is the distance of the 0th frame and the second frame, end effector frame, along y0. And this is the distance between the 0th frame and the end effector frame along z0. This is very easy to understand. We can see just from the geometry that is correct. Now let's try to see if we can provide some geometric interpretation to these values. So I'm going to switch screens again. So the MATLAB will not be visible. So before I go on to the geometric explanation, I just want to make sure that everyone got this answer. Online students, because it would be difficult for me to again switch back to discussion, the MATLAB. So if your code is not working, if you want to see the code, this is the time. Okay, so now I'm going to switch the screens. So, and here is what we have to begin with. So what I want to do is, I want you to look at this figure. And I want you to think about something like, if I were to look at this robot in the top view, if I were to look at this robot in the top view, what would I see? And if I were to look at the robot in the front view, what would I see? So in front view, it's very easy. I know my end effector is at location 2. So the distance between the end effector and the first frame or 0th frame is nothing but A1 plus A3. So which means I will just draw the vector. So that will kind of make sense. So if I were to draw the vector, it's going to be something like this. And this direction of this vector, please note, is deliberate. This direction is aligned with this direction. Everyone understood this? Now what I'm going to do is I'm going to look at this robot in the horizontal direction, and I will draw the robot in the horizontal, in the top view, something like this. Let me draw it over here. So my coordinate frame is x0, y0. Do you agree with me? This is my 0th frame. So I have A2, and this is the angle θ1. And then I have A4, and the important part is here. This is a very, very important part. The way we have defined our coordinate system, this is my θ2. So I have θ1, and this is my θ2. So what I'm going to do is I'm going to use the projections, and everything will be super clear. This is going to become cosine θ1. If you look at this angle is same as θ1. So the projection, this guy is going to become A4 cosine of θ1 plus θ2. So which means the total distance, horizontal distance, is going to be A2 cosine θ1 plus A4 cosine of θ1 plus θ2. Can you check your MATLAB code and tell me if that is the answer we got? Right? Next thing, same logic here. This distance is A2 sine θ1. This distance is A4 sine θ1 plus θ2. Now I want you to look at your homogeneous transformation, 4th column, 2nd row, and tell me if that is the answer you got. So everything checks out, which means the homogeneous transformation matrix forward kinematics that we solved is same as what we got here. Now, since we have come so far, what I'm going to do is I will kind of tell you what can be done from this point onwards. You have the expression for the position in x0 direction. You have the expression for the position in y0 direction. You have the expression for position in z0 direction. If you take the derivatives, you would get the velocities. The easiest velocity to find out is the velocity in z0 direction. Can you see that A1 is constant, A3 is constant. So if I take the derivative, that means the velocity of the end effector in z0 direction is 0. Does it make sense? But if you were to find out the velocities in x0 and y0 you have to use the chain rule because there is the dependence on theta, theta 1 and theta 2, and theta 1 and theta 2 are dependent on time. So you will have to use the chain rule. And to be honest with you, you don't have to do it by hand. Once you set up the problem correctly, MATLAB will do that for you. Any questions on this problem? Everyone understood everything? Okay, since let me take another problem. So in this problem, I'm gonna have a robot wherein this is the first revolute joint. Then I would have a second revolute joint. And then a third revolute joint. I mean, actually, yeah, I'll add a third revolute joint. And there are many cases possible. So as you can see, all the possible cases you can think of, you can solve with this technique. And something to tell you, this is not the DH parameter technique. This is called as the rotation matrices. This is not the DH parameter. This technique always works. So even if you have DH parameters causing some singularities, and we'll talk about it, you cannot use DH parameters. But this technique will always work. So first and foremost, can someone tell me the first rule? What is the first rule? Remember, there are 4 rules. Okay, so G naught. Second rule, okay, let's finish the first rule. Z1, Z1 can go out or Z1 can come in. Doesn't matter as long as it's along the joint axis. It's good. Z2, and just to make my life easier, I'm gonna add Z3. Then I'm gonna have X naught.
But it has to be perpendicular and intersect, right?
There is no frame before Z naught. There is no frame before, so it doesn't matter. It doesn't matter. There is no frame before. So there is no harm in having X naught like this. Or there is no harm in having X naught in this direction. There is no harm in having X naught like this. It doesn't matter because there is no frame before 0. So for first frame does not matter. So X naught at this point, right hand. Why not? Now here, it's very important. So what is the second X1? And I will write this down. X1 should be perpendicular to Z1 and Z0, and it should intersect. This is a very important rule. So I want you to think about for a second and tell me where these 2 rules are satisfied. So, and I'm gonna make this mistake one more time, just this once, so that you don't make that mistake. There is a possibility that someone may say that, oh, why not? Oh, good. I will just choose X1 like this. Because this X1, though it is perpendicular to Z1, this means the first part of rule 1 is satisfied, but it is not perpendicular to Z0. Do you agree with me?
Right.
So do not make this mistake. Otherwise, your forward kinematics, inverse kinematics, forward dynamics, inverse dynamics, everything will be wrong. And we will use the exact same rule for DH parameters. So basically, you don't have to remember 2 sets of rules. These are the rules. Now I'm going to assume X1 like this. And once I do this, complete the triad. Curl your, actually right hand thumb rule, X Z, Y going up. Right hand. Everyone understood? Oh. Do we need to assign frames in order to solve the problem, or they will be pre-assigned? Okay, this is what happens. And I'm very, very serious. If you pick up a problem from the textbook, they will give you some random frame assignments. And I'm going to do that same thing. When I'm going to assign, actually, as a matter of fact, I did that in one of the assignments. I gave you some random frame assignments. Those frames do not follow any of these rules, or may follow a couple of rules, may follow just 3 rules. Whenever you get a robot, first draw the kinematic diagram and set your own frames. Do not follow the frames that are given on the diagram. Set your own frames. Make sure all these 4 rules are specifically satisfied. If they, and I can tell you, there are tricks. You can have robot arms or robot, they are given at an angle. So then the question comes, how do I make those perpendicular? And I will talk about it. But to solve forward kinematics problem, you must satisfy these 4 rules. If you look at any problem in the textbook, if these 4 rules are not satisfied with the frame given, cancel out those frames and construct your own frames. Those are frames of reference. Those are for your convenience. Everyone understood this? And in the, I think in a couple of assignments, I gave you some weird frames just to confuse you. But do not look at the frame, draw the kinematic diagram, and then draw your frames. How do I specify this robot? The first revolute joint is perpendicular to second revolute joint, is parallel to third revolute joint. So this robot is R, perpendicular to R, parallel to R. Now for the second, again, see if this makes sense.
No. It does? How come on this one, we don't have to be, X2 doesn't have to be perpendicular or intersect?
Okay.
Oh, shoot, it is perpendicular to it. Oh, Jesus. Yeah. My bad.
Does anyone else have any question? Okay, the last. And it's very tempting for me to solve this problem completely. But what I'm going to ask you to do is I want you, I will solve this problem completely, and I will solve a MATLAB solution. I'll show you the solution using MATLAB. But at this point, I would like to give you a couple of minutes to write homogeneous transformation matrices. So please try transformation matrices. And they are easy. R01 is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. However, you must be super duper careful on the projection matrix. This is projection of x1, y1, z1 onto x0, y0, z0. Now, for a minute, I want you to think about it. X1 is in the same direction as x0. Y1, and this is super important. Everyone look at the board. This is super duper important. Y1 is not in the direction of y0, but it's in the direction of z0. So this is 0, this is 0, this is 0, this is 1. This is something that I want you to remember. The last part is this guy, and this is actually even Z1 is in the direction of Y0, but the arrows are opposite. Which means I'm going to take a shortcut here. So everyone look at the board. I'm going to take a shortcut here. So what I usually do is this at this point, I write my homogeneous transformation matrices. Cosine theta 1, then this becomes sine, so actually this becomes 0. Let me actually do this calculation for the first time. Okay. Let me not skip steps here. We will do that in the next problem. So first row, first column, cosine theta 1. First row, second column, 0. First row, third column, which is sine theta 1. Second row, first column, sine theta 1. Second row, second column, 0. Second row, third column. Third row, first column. Third row, second column. Actually, third row, second column should give me 1. And third row, third column. Now I want you to make sure that the sanity check works out. So can you see this is 1? So yeah, this works out. Now, this would be a perfect time to write homogeneous transformation. Cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1, 0, 1, 0. And I'm going to start. I didn't give you any distances, but I will now in just a second. This is A1. So this is going to become, can someone tell me what the position gonna look like? 0, actually 0, 0, and A1, 0, 0, 0, 1. And I'm gonna stop here.